Okay, my name is Mark Wise. I'm a professor at Caltech, and I'm going to give you a small lecture today on an application of heavy quark symmetry to the semileptonic decays of B bar mesons to D and D star mesons. So it sounds like a very particular problem, which it is, but it has a lot of important consequences. So let me sketch out the basic problem first, and then I'll walk you through how you use heavy quark symmetry to get some information on it. So we're interested in a particular physical process. That's always the way it is in physics. And we imagine an initial state, which is a B bar meson. A B bar meson contains a bottom quark and a light antiquark, and then all kinds of light degrees of freedom, gluons, quark-antiquark pairs. But the basic quantum numbers of the state are carried by the B quark and the antiquark. And the B quark can transition to a charm quark through the weak interactions, emitting a virtual W boson, a W minus in this case. And that W minus materializes to an electron and an antineutrino. And here we have in the final state either a D meson or a D star meson. The B meson and D meson are the lowest mass mesons that contain bottom quark or a charm quark, and therefore they decay weakly. And this D star meson is closely related to the D meson. It's just a different spin combination. The D meson and the B bar meson have spin 0, and the D star meson has spin 1. So this is a process that occurs in the standard model. I've had the W boson minus, virtual W minus materializing as the electron and its antineutrino, but of course it could also be a muon or a tau. And we know the structure of the vertices from the standard model. At this vertex here, there's a left-handed current, gamma mu, 1 minus gamma 5, a factor of the weak coupling, G2. Usually combine those with some factors of the W boson mass to make what's called the constant G Fermi. But there's also some weak mixing angles that we'd like to know. The weak mixing angles are parameters of the standard model, so we certainly want to know them. But it's possible eventually we'll have a more complete theory that makes predictions for those quantities. And it might be the level of our understanding of the value of weak mixing angles that tells us whether this extension of the standard model is correct. So we've got a theory of the standard model. We should know its parameters as well as possible. Also, and that's one way in which the predictions I'm going to make are used. Also, you can search for new physics just in the structure of these decays, so it's important to understand them. Okay, so what do I mean by understand these decays? There's a decay rate. You can form a differential decay rate. There's basically two variables that characterize the final state, so you pick whatever two variables are convenient for you. A lot of this physics is perturbative and known. This part of it is all known. The W boson couples with vector and axial currents. And it's the matrix elements of those currents in these hadronic states that's the thing that's difficult to know. For example, I've drawn this as if it's a Feynman diagram, this object here, but it's really not a Feynman diagram. It's more like a Feynman cartoon. You've noticed I've mentioned Feynman a lot of times already. That'll happen over and over during this lecture. I'm a Caltech professor, and I get a very small pay increment every time I mention Feynman's name. I have to participate here in Caltech branding in addition to MIT branding. But anyways, back to the physics. Why is this a cartoon? Well, I've drawn nothing that refers to the strong interactions here. Of course, you could have a gluon here. Makes the diagram more complicated, or a gluon here, or I could have the 4-gluon vertex here, et cetera, and all of a sudden, it's pretty lousy to think about this process in terms of Feynman diagrams. You got to add them order by order in perturbation theory. These bound states clearly involve non-perturbative strong interactions at the scale lambda QCD, a few hundred MeV. That's what's involved in the binding of the antiquark to the heavy quarks. And so really, all I can say without understanding some non-perturbative aspects of the strong interactions are what symmetries that we know tell us about the matrix elements of the currents that are needed. So here, I tried to put a few of the longer equations on the board ahead of time just to save time. So what enters here is a B-bar meson. Here's the current, the vector current, a vector current, an axial current. On the right-hand side, the strong interactions conserve parity and time reversal. Everything conserves Lorentz invariant as far as we know. So on the right-hand side, you just try to make some parametrization of these matrix elements consistent with those symmetries. You know how the currents transform. Consistent with those invariances. And in addition, of course, Lorentz invariance. And basic things in quantum mechanics which tell you that the polarization vector must enter linearly as epsilon star. So you just characterize those matrix elements. And the things that the matrix elements are expressed in terms of, the Lorentz invariant parts, are called Lorentz invariant form factors, or just form factors. So here Q is the momentum transfer. Q would be equal to P minus P prime as a 4 vector, where P prime is the 4 vector momentum of the D, or D star, and P is the 4 momentum of the P, so they square to the mass squareds of the states. And of course, P prime dot epsilon is equal to 0. So the form factors, the 6 of them, F plus F minus G, F, A plus A minus, they're just some functions of Q squared. Q squared is a scalar. And then I just write out all the possible things that transform in the right way to represent these currents. If I look at a differential decay rate, it can be expressed in terms of all of these form factors. So they're the things that we need to know. Looks like a pretty complicated thing. There's a lot of form factors. Of course, you can measure them from the data, and they have been measured. But I'm not going to talk about the data in this lecture. This lecture is really about the theory of these decays, and in particular, what heavy quark symmetry can tell us about these decays, and that amounts to what it can tell us about the form factors. So here we are. That's all we know in terms of the fundamental theory, in this case QCD, theory of the strong interactions. We just know that all these matrix elements are parameterized in terms of these form factors. Now there's some arbitrariness in this parameterization, unfortunately. For example, do I put the I here or the I here? I could take these states, the pseudoscalar states, and multiply them all by an I. And that might change where you put the I, and if you look at one book or another, there can be a different convention. Can't help that. That's, some things are just convention. In the end, you have to take the absolute value squared of the whole thing, so those things cancel out. And of course, the initial state's always the B, because the B star doesn't decay weakly. The final state can be the D or the D star. So those are the matrix elements we're interested in. And now, there's not much more I can say in full QCD, so I got to go beyond that and look at the heavy quark limit of QCD. So we're going to go over to the heavy quark limit, and that has already been introduced to you. And in the heavy quark limit, quarks of the same velocity, different quarks, let's say charm and bottom. If they have the heavy quarks will end up being the charm, the bottom, and the top. And they're heavy in the sense that their masses are much greater than the scale of the strong interactions, lambda QCD. And so it gets better and better as you go charm, bottom, top. Unfortunately, the top decays weakly. It doesn't even basically form a strong bound state. It decays. Its lifetime is so short. And so the methods that are related to heavy quark symmetry aren't very useful for the top. It's kind of ironic since it's the heaviest quark of all. So they're really used for the charm and the bottom quarks. So if I have a heavy quark, Q, that heavy quark can have some momentum, and if I take out the mass, some 4 velocity. And you can take the limit of the Feynman rules of QCD or the limit of the Lagrangian, the part involving those quarks, and easily see that the interactions of those heavy quarks are independent of the heavy quark spin and independent of the heavy quark mass. One important feature of this is they're independent of the mass when we're looking at heavy quarks with the same 4 velocity, but that means different momentum because there's a factor of mass in the momentum. Another important feature is that the strong interactions, when they're involved in binding, let's say, light degrees of freedom to the heavy quark, the momentum of those light degrees of freedom is very low compared to the heavy quark mass. And so this velocity is basically unchanged by these strong interaction processes. In the heavy quark limit, where we neglect corrections suppressed by powers of the strong interaction scale, lambda QCD, divided by the heavy quark mass, this velocity, we're usually going to use a 4 velocity, so v squared as a 4 vector is equal to 1. This 4 velocity is just a label. It stays fixed. It never changes by the strong interactions. Of course, in this process here, when we go over to the heavy quark limit, which is what we want to do, basically we want to go over to the heavy quark limit, and we want to see what the new symmetries that exist in the heavy quark limit have to say about the problem. Because the interactions of the heavy quark are independent of its mass and independent of its spin, there's a spin flavor heavy quark symmetry. And we could try to exploit that symmetry in the heavy quark limit to say additional things about these form factors. That's where we're headed. That's the name of the game. And we'll see how far we can get. Now, even though the strong interactions don't change the 4 velocity, the W boson, it's some external object to this problem. It comes in with some really big momenta of order of the heavy quark mass, and it takes this heavy quark at some 4 velocity, the bottom quark, and just changes it to a charm quark at a different 4 velocity. And of course, when the 4 velocities are different, then the symmetry won't relate the two. But still, we have some power associated with that, and you'll see it's considerable power. So I want to talk a little bit more about the hadronic states in the heavy quark limit. So as I mentioned, the spin of the heavy quark is conserved. The interactions don't depend on it. And usually we label hadron, some bound state containing strongly interacting particles. We label the hadron by its spin. For example, the pion has spin 0, and the rho meson spin 1, etc. The D star meson has spin 1. But now, because the spin of the heavy quark is a good quantum number, we can talk about the spin of the light degrees of freedom. The total spin, the usual quantum number, is just the spin of the light degrees of freedom plus the spin of the heavy quark. The spin of the heavy quark is a half. And so basically we're going to get states with total spin that's equal to the spin of the light degrees of freedom plus or minus a half from adding the heavy quark spin into the problem. And so hadrons in the heavy quark limit come in these doublets. And these doublets are degenerate in mass in the heavy quark limit. Of course, the D and D star, their masses aren't exactly equal. They are split. But that splitting is suppressed by 1 over the charm quark mass, something of order lambda QCD divided by the heavy charm quark mass. And the splitting is even smaller between the B and the B star because the bottom quark mass is heavier than the charm quark mass. Okay, so we've got these multiplets. In this case, for the problem of interest, the multiplets are the B and B star and the D and D star. And these multiplets have spin of the light degrees freedom equal to a half. That's the simplest thing you could have for a meson that has an interpolating field with a light antiquark. It's basically the same spin as the light antiquark. Of course, there are other hadrons, excited hadrons, that have maybe 3 halves here for the quantum numbers for the light degrees of freedom. But it should be no surprise that the ground state, the lowest hadrons, that have an interpolating field with a B and a light anti-quark have the same spin at a light degrees of freedom as a light anti-quark. Should cost some energy to get excitations above that. Okay, so when we go over to the heavy quark limit, we label the heavy quark by this 4 velocity, and the heavy quark field is constrained. It's really just a quark and not the anti-quark, so it doesn't really have 4 independent components. V slash on it, it gives you back itself. That's basically the big part of the Dirac equation that involves with the heavy quark mass factored out. So if I want to use heavy quark symmetry to try to make predictions for these matrix elements, there's probably a better way to convey the relevant physics, because, for example, all these factors of momenta and q squared, they all involve the heavy quark masses. And we know that the physics becomes independent of the heavy quark masses in the limit where the quark becomes heavy. So we want to find a better way to write things. And because I didn't want to spend the time writing a lot of big equations on the board while I'm giving the lecture, I took another equation and put it on the board ahead of time. But we'll have to work up to that equation a little bit, so just hold on. So I'm going to want to use 4 velocities, and so I'm going to introduce for this problem. We start with our bottom quark. It's going to go to a bottom quark labeled by a 4 velocity V in the heavy quark limit, and the charm quark will go to a charm quark labeled by the 4 velocity V prime. The D and D star mesons, I want to label them by 4 velocities too. So for example, P I'll take as MBV, and P prime as MD. Doesn't matter whether it's D or D star, or even the charm quark mass for that matter in the heavy quark limit, but we'll take it to be this mass times V prime. So just a little bit more. Our states. Our states have factors of the heavy quark mass in them because we usually conventionally normalize things to twice the energy. The energy has a factor of the mass in it. So basically I want to introduce states, for example, B of V. Let's do the bottom. That would be the usual one. And then I'm going to divide by square root of the bottom quark mass, so of the B meson mass, so this left-hand side doesn't have any quark mass dependence, and similarly for the other ones. So I'll just put etc. So now I got the left-hand side. The matrix elements I want to calculate, now not in full QCD, but in the effective theory. I should have said one more thing. I've chosen to evaluate all the fields, the quark fields at the origin of space-time. Otherwise, the matrix elements have some simple dependence on space-time that you can get from translational invariance. So I just evaluate them at the origin, so I don't have to worry about that. So all the fields are evaluated at the origin. So this right-hand side now is independent of the heavy quark mass, because the dynamics of the strong interactions are independent of the heavy quark mass, and these are just some strong interaction matrix elements. Once I factor out the W boson propagator and stuff in the Feynman diagram, this is just strong interaction physics. So again, there's certain form factors, and you parameterize this using the parity invariance and time reversal invariance of the strong interactions and the Lorentz invariance of the theory, knowing how these currents transform under parity and Lorentz invariance. Is the same spiel as before. But now I don't want to write this side in terms of momenta because the whole thing's independent of the heavy quark mass. And why would I introduce this dependence that I know has to cancel out? You'd have to be a raving lunatic to do something like that. And I try to avoid that designation. So I don't want to use q squared here as my Lorentz scalar that my form factors depend on. The conventional one to use is W equals v dot v prime. So in the rest frame, for example, when the final meson is at rest in the rest frame of the decaying B bar, then these four velocities are the same, and W is equal to 1. Q squared at that point, for example, is just MB minus MD, maybe star, if it's the D star meson squared. So these two values of these Lorentz invariant quantities, these scalar quantities, correspond to the same kinematic point. Okay, so let's think about things we might know. So we have all these additional symmetries. We have this spin flavor symmetry. A spin up charm quark can be transformed to a spin down bottom quark. And that should have some power for these matrix elements. We want to understand that power. So one thing that happens with symmetries is there's certain charges or charge densities, and you know the matrix elements of the charges. That's a common thing. Think, for example, of isospin or electromagnetic charge. That's usually used to normalize some form factors. No different in this case. So if I look at this operator here, C bar V gamma naught BV, this is a charge because of a knot component. It's a knot component of a current. It's a charge for the flavor symmetry. That changes a bottom quark to a charm quark. Have to be at the same 4 velocity. Well, same 4 velocity, same 3 velocity. Same velocity because it's quarks of the same velocity that have the same properties independent of their mass and spin. And so, or independent of their flavor. And so if we look at this matrix element, these objects, B and D, are in the same multiplet under the spin flavor symmetry because I've just rotated bottom to charm. That matrix element, I know. I know the normalization, and it's equal to 2. So here now I've written out the form factors. I had the F's and the G's, and now I've written them in terms of H plus, H minus, HV, and the HAs. It's just another parameterization. These you could put in the factors of momenta in terms of velocities and write the linear relations between the form factors. There's no more physics when I write it like this, except the fact that both sides are independent of the heavy quark mass, which comes later. Okay, so I know this matrix element. We could ask ourselves, what does it imply in terms of these form factors? So if you look at it, I looked at this one here. V is equal to V prime, so this one's 0. And it just tells me that H plus of 1 is equal to 1. So it's a very simple relation. It's not a complicated relation at all. Of course, all the physics is in the one above, so I could ask what it looks like if I use the original form factors. So let's write it out. So it's the first line. It's something about F plus and F minus. I just go to the kinematic point where they're both at rest. And so I get F plus at MB minus MD squared times MB plus MD plus F minus of MB minus MD squared. And then I get MB minus MD. And then I got to divide by the square root of MB MD. And heavy quark symmetry tells me at leading order that this is equal to 2. Okay, so I'm asking you, class. Unfortunately, you're not here. We got 2 ways to parameterize things. In one way, the prediction looks like this. In the other way, it's this god-awful, disgusting mess below it. So obviously, we're on the right track by writing things in this way and thinking about things in terms of the heavy quark spin flavor symmetries. It was the flavor symmetry that led to this prediction. So now I want to exploit the full power of the spin flavor symmetries. Remember, the D and the D star are related by the spin symmetry at the same form velocity, which is here. So there should be relations between these form factors. More than just this relation at a particular kinematic point, there should be relations between these form factors. We don't know to start with how many relations there are, but there should be some. So I want to derive those relations. There's a straightforward way to derive them by forming the generators of the symmetry and taking commutators of those generators with the currents and working out what that gives you for the matrix elements. These predictions were originally made by Nathan Isker and me. That's the way we did it. But then there was some very beautiful work by Georgi and Bjorkane. And they showed independently a much slicker way to do the group theory, in addition to physics, of course. But the thing I'm going to use from their work here is this very slick way to do the group theory to get the relations. But now it's basically a group theory problem. How do we derive those relations, given that we know how these things transform? So let's just do it. So the trick is, yeah, I'm bored rich. The trick is to put the mesons, so let's say the D and D star mesons or the B bar and B star mesons, to put them together, introduce interpolating fields for them. So the D or the B bar is a pseudo-scalar, so I'll denote it PQ. Q could tell us which heavy quark. And the other one in the multiplet is the vector meson, so you put a star on it. Where did I put the stars? I put the stars after the Q. Doesn't matter. And it's got an index mu. It's a vector field. And they're labeled by a 4 velocity v. And so these are, if you'd like, interpolating fields for those mesons. And we want to combine these two interpolating fields into a single object. And the reason we're going to do that is because they mix up amongst themselves when you apply the spin symmetry. So we want to have all that encoded in a simple way. And once that's done, the group theory becomes trivial. It's good to make the math trivial. So how are we going to do that? Well, let's go back to the quark level and think about the following bi-spinner. You could think about this bi-spinner as being an interpolating field that creates the hadrons. And what we're going to do is replace it by an object that contains these fields, both of them, linear in each of them, which I'll call H alpha beta. So however this transforms, this is a bi-spinner. These are spinner indices. This is a bi-spinner. It's got the velocity label and the heavy quark label. And I got to put in the meson so it has the right transformation property. The thing is, we know how this transforms under all the relevant things. We know how it transforms under Lorentz transformations. That tells us how this transforms under Lorentz transformations. We know how it transforms under parity. That tells us how this transforms under parity. We know how it transforms under heavy quark spin rotations, for example. A spin rotation R, QV would go to the matrix dq. It's a 4x4 matrix, dqr times q of v. And these matrices, for example, satisfy gamma naught d of r dagger, gamma naught d of r inverse. And so under this same rotation, because that's how q transforms, I know right away that v sub q goes to this d of r h v of q. So with this understanding, it's really easy to understand how h transforms under all the relevant symmetries of the strong interactions. We also have the further constraint that this is a heavy quark, so it satisfies v slash on qv is equal to qv. And so we know this hv is going to satisfy v slash on hvq is equal to hvq. So now we just got to stick these things into H, write it in some way that has all these right properties. We also know how these things transform under the symmetries. And I'm just going to write down the answer for you. You can check that it's true. It's almost obvious that it's true. One of the worst words in physics, obvious. At one time it was obvious that parity was conserved, and then we found it wasn't by the, of course that's physics obvious, not mathematics obvious, but same types of mistakes happen in both cases. Anyways, so I'm just going to write it down. I'm not going to go through the exercise of checking all this. There just isn't, there isn't the time for this in a short lecture like this. And I'm not a fast lecturer. I don't cram a lot of stuff in the lecture. And you can find more details in any good book on this subject. I could recommend one. For example, this book by Manahar and Wise on heavy quark physics. Yeah, a shameless plug. Okay, so let me write down HV of Q. So I got to put in the various mesons. So there's the pseudoscalar meson interpolating field. It has no Lorentz index, so it'll just sit in there. It's a pseudoscalar, so if you look how things transform under parity, you got to have a gamma 5, and my convention is the I. Some people might not have the I. That's their business. I'm putting an I in. But that's just convention. Then I got to have the vector. It's a vector, so no gamma 5s on this part. I got to contract the index, so let me use a gamma mu matrix. And then there's the star. Geez, this notation's kind of cumbersome. And that's it. So, that's it. Maybe I should write a sensible equation. There's a plus sign. That's it. We've now included them into this matrix HV of Q. So now how do we do the group theory? How do we do the group theory? Well, let's say we have a current, either the axial or the vector. I'll combine them all together by just calling the gamma matrices capital gamma. So it could be gamma mu, gamma 5. Or we could do other cases as well, except if we wanted to say, for beyond the standard model of physics, what about a charged Higgs? Then there'd be scalars there. Maybe a 1 or a gamma 5. So we have an object like this. And let's say we make a transformation under a heavy quark spin rotation. Well, then we know this is going to go to C bar V prime D for the charm quark, our inverse gamma D of our B of V. And so the current's not invariant under these spin rotations. As physicists, we're awesome at constructing invariants because the action's an invariant under things like all the symmetries you want. So we like to think about invariants. And so there's a trick to do the group theory that is often used in physics. I think it might be called the Spurion trick. These gammas, they're gamma matrices. They're not fields. They don't transform under heavy quark spin rotations. But you just pretend they transform. You endow them with the following transformation property. Once I endow them with this invariant transformation property, then the current is an invariant. So now I know what to do. I got to construct a, of course, this is not going to be, I'm going to write down a formula. It's a formula as a trick to do the group theory. It's not meant to be a formula in the usual sense. You're just supposed to use it to do the group theory. What I'm going to do is I'm going to express this current here in terms of an H for the B and B star, an H for the D and D star, and I'm going to put it together in a way that it's invariant under the spin rotations, if I imagine the gamma matrices transforming this way, and has the right transformation properties under Lorentz transformations and and parity, etc. And then how do I use it? I'm going to want to take its matrix elements in the end between these states here and this D star here. So the initial state is always a bottom. And so when I have the HVB here, I'll just put a 0 here. And when this will be PVB, and when it hits the B meson state, it just gives me a 1. And for the final state, if it's a D star matrix element, I'll put the D star here. And when it creates the final state, it just gives me the polarization vector for this. And then I'll put the D to 0 for that matrix element. And for the matrix element involving the D, I'll set this to 0 and put the D here, and it gives me a 1. So that's how I'm going to do the group theory for those matrix elements. So all I have to do now at this point is figure out the most general thing I can write with an HVQ. It's clearly going to be, well, the most general thing I can write. So now I got to write another equation for you. And let me write it out, and then we'll say more about it. Uh-oh. Geez, if I wouldn't have wrote so giant size, I'd have more room. OK, so let me go over to, let me erase some. I'll erase this part here. OK, so now what do I want to introduce? Well, I'm going to have to introduce something that I call H bar, because I got a C bar. So H bar is just the usual thing, gamma naught. And, oh, I should have said one more thing. This HV now satisfies, of course it had to, because of the interpolating field interpretation, HVQ equals HVQ. But it actually satisfies something else. If I put the V on the other side, I can move it through the gamma 5. It gives me a minus sign. I can move it through here because V mu P Q star mu is equal to 0. This is the transversality of the polarization vector again. Because of this constraint, I can move it through. I can move it through here, anti-commuting it through the gamma matrix, and the anti-commutator gives the V mu, which gives 0. And so you'll find that this is equal to minus HVQ. So that's just a consequence of the parametrization. This is sort of the important fundamental thing we had to build in right away with this 1 plus V slash over 2. So we're going to need to introduce H bar. And it's going to satisfy, for similar reasons, V prime slash on HV prime C bar is equal to minus HVC bar. And when it's on the other side, it'll give you the plus. OK. Shouldn't be looking down at my notes all the time. But now we're ready. We're ready to construct what we want. And so if I have a current like this, it doesn't even have to be a current, any collection of gamma matrices here, then I'm going to represent this by, maybe I'll put an equals. Remember, it's not a real equals. It's equals only in the sense of doing group theory. A trace, something here which we'll talk more about. So whatever gamma matrix is here goes here. That's what has the same transformations of the currents. Can't put anything else between here, because then it wouldn't have the heavy quark spin invariance. But I can put whatever I want here. I have some freedom for what I put there. So for example, it could just be a function of W, the dot product of P with P prime. But I could also put anything else that won't change the Lorentz transformation properties. So I can put x1 v slash. But then it's a trace. I could take the v slash over here, and I would get minus this. So this is really not independent of the x naught. I don't need to add it. So We'll cross it off. And similarly, the other things you could imagine adding, like x2, v prime slash, that one could act here, so I don't need that one, it's the same. And plus x3, v slash v prime slash, similar reasons we don't need this one. And so basically, there's just one independent function that characterizes these matrix elements. The convention's not to call it x0, but usually it's called minus c of w. So this function characterizes all the matrix elements. So what have we learned? We've learned there's only one form factor, one independent function that characterizes all the matrix elements. Not just vector, axial vector, but pseudoscalar, scalar as well, because it didn't matter what gamma is. Put whatever you want. Put sigma mu nu if you want, the tensor ones. They're all characterized by this single function. And all you got to do to calculate the matrix elements is take this trace with the h's that I've written down and replace these by either a 1 or the polarization vector, depending on the particular matrix element at hand. So that's an exercise you can do. And let me tell you what you get when you do that. So we can now return back to these form factors. You're going to get some prediction for these form factors. So I'll write it out for you. Well, I hope I took the traces correctly. I didn't look in the book. And the normalization condition just becomes the fact that this is equal to 1. So a lot of predictive power. All the form factors are expressed in terms of a single form factor, even for the different processes B to D and B to D star. This is the prediction at leading order, where you take the masses as very large. But once you've got a method like this, of course, you can expand beyond leading order and try to characterize what you would know about the matrix elements. And there's still some predictive power. That's been done. And for heavy quarks, at least, this is a very powerful tool. It's kind of a standard tool that you should use under those circumstances. If you do beyond the standard model physics and you have a long-lived color particle, if it was a scalar, you could also take the Hemi limit for that, and its interactions just depend on its color charge. So you could put more things in the multiplet. I hope you've enjoyed this short introduction to an application of heavy quark symmetry. Thank you.